Hi everyone. Today I'm going to tell you about the automatic program inversion using symbolic transducers. The first thing I want to do is motivate you why we might care about the program inversions. In this slide, you can see in the left-hand side is some plain text, and for communications, information processing, or security purpose, we may want to encode them to, for example, base 64 encoders to the code shown in the right-hand side. And of course, for each encoder, there exists a decoder which can recover the plain text for us from the code. And one may think this is simple to write such programs, the encoder and decoder, but sometimes things don't go well. My advisor, Lois D'Antoni, whose name contains a single quote, sometimes he received email like this. If you can see, the single quote was encoded to the HTML code, but wasn't decoded correctly. Such bug annoys him all the time. And the bug in the encoder and decoder may cause a more serious security problems. In Stack Overflows, the URL of the profile picture is provided by the users. And an attacker, if the decoder doesn't work correctly, an attacker can put the unescaped single quote and inject arbitrary codes to the URL, which is called cross-site scripting attack. So we want to write encoder and decoder correctly. To better understand the problems, let's go through a quick example of base 64 encoders. Here is the base 64 encoders. Each time it reads 3 characters. In our example, it's M, A, and D. And it divides the 424 bits to 4 fragments. Then it maps each fragment to text characters by these map tables. This is the base 64 encoder wrote in our domain-specific language, Genic. You don't need to understand this program. I just want to show you what features we need in the encoders. Firstly, we want some auxiliary functions at the top, and we may use the pattern matchings to read characters, and we have some output functions and tail recursions to output symbols. This is the snippet of the decoders of it, and which looks similar to the encoders. It also has auxiliary functions, pattern matchings, and output function for each case. However, we may sometimes want to adapt our encoder to different encoding schemes. Some constants may be changed, and the pattern characters, which is used to make sure that the length of the code is divided by 4, may be deleted or modified. For the simple modifications shown in this slide, let's look at what happened to the decoders. In this case, we need to write new auxiliary functions, new pattern matchings, and new output function for each pattern matching case, which make it just like a new programs. D'Antoni and Venance have shown how to verify the encoder and decoders are inverse of each other's. However, writing both programs are still time-consuming. Therefore, a natural question arises. Why don't we just automatically synthesize the decoder from a given encoder to avoid repeating works? The answer is yes. So we built a tool Genic, which can automatically synthesize the inversions of programs such as encoder and decoders. Now, let me tell you how the Genic works. I will now first introduce the program inversion problem formally, and then explain how Genic works. Firstly, let's look at what is program inversions. What does the inversion mean, and when we can invert programs? First, we ask, what does it mean for an encoder and a decoder to be inverse? It means that if we run the decoder functions to the output of encoder, we will get back what we start with, and similarly, the same happens when we run the encoder to the output of the decoders. Now, someone may ask why we need both directions. Only if both directions holds, the domain and the range of the encoders and decoders has the relationship shows in this diagram. In particular, the domain of the encoder should be equivalent to the range of the decoder and vice versa. Then the second question, when can we invert a program? First of all, the program should be injective. If the function of a program encoder is not injective, for example, in this example, the encoder will encode ABC and capital ABC to capital ABC, and in this case, we don't know, we can't decide what the decoder output when you read capital ABCs. Second, even if the encoder is injective, the inverse of it might not be expressive in our programming model. For example, the x minus sin x is injective. By its inverse, we cannot express its inverse in our programming models. In general, we can't invert arbitrary functions, arbitrary programs. So if we still want to invert programs, we have to restrict our focus to a simpler programming models. The simpler programming model we choose is symbolic extended finite transducers. Before introducing the symbolic extended finite transducer, let's revisit the encoder functions and see what features we need to model it. Still these programs. Firstly, we want some bit vector manipulations, and we want it support something like the pattern matching, which can read multiple characters each time. And at last, the model should be able to recursively process the tail of the input being read. Then let's look at the symbolic extended finite transducers to see why it is expressive enough to model the encoders. A symbolic extended finite transducer is a kind of the finite state systems which contains finite number of states, final states, and transitions. Here is an example transitions of it. Firstly, the transition can read multiple characters each time. For example, 3. And then, second, the transition will be applied only if its predicate phi is valid on the input. In this example, the input should be bit vector with length 8. And if the predicate is valid, it will output some characters using this output function f. Then, in the base 64 example, we start from the state Q, P, and we read 3 characters, x1m, x2a, and x3d. And this input valid the predicate, so the output function is applied and output the 4 characters t, w, f, k to the output buffer. And at last, we transit to the next state Q and repeat this process. Symbolic extended finite transducer operates on characters derived from the background theory of terms T that close under Boolean operations. So if we want to have good properties, we can choose the Boolean algebras such as bit vector arithmetic or linear integer arithmetic. So the transducer is strong enough to model the encoders and decoders. And the next question is how to invert an injective transducer encoder. Firstly, we need to firstly check its injectivity if it is injective, and then we need to compute another transducer decoder such that the composition of encoder and decoder is identity, and their domains and range satisfy the property we described before. Now let's look at the first task, checking the injectivity of a transducer. Intuitively, a transducer is not injective only if 2 different inputs can produce the same output. To check these properties, we can construct its output automaton by replacing each we can construct its output automaton like this by replacing each transducer transition to an automata transition. In this transition, the below one, the automaton transitions, you will read the input X if and only if there is C on A, such that the transducer transition can read the input A and output X. That is, X is a possible output of the original transducer transitions. Then let's try to define the injectivity with respect to the output automaton. A transducer is injective if and only if there are no two distinct accepting paths for the same input in its output automaton, which means that its output automaton is unambiguous. However, checking the ambiguity of a symbolic extended finite automata is undecidable. So checking the injectivity of the transducer is undecidable. Although we can't check the ambiguity of arbitrary automaton, some automata have good structures, and we can check the ambiguity for them. In particular, the problem becomes easier if the predicate of the automaton can be expressed as a Cartesian predicate, which can be written as the conjunction of predicate reading one characters. Then we can then split each transitions of the extended automata to several transitions which we start look at and lead to a symbolic finite transducer, non-extended one. And therefore, checking the ambiguity of a symbolic finite transducer is decidable. And this is the case in our problem. The decoders and encoders in our problem, their output automaton is Cartesians. With knowing how to check injectivity, our next task is how to compute the inverse of the transducer. To invert transducers, we first look at the transitions in these transducers. Given the transitions from P to Q, we look at L and predicate phi, output function F, what its inverse look like. First of all, its inverse should also be a transducer transitions from P to Q and have a predicate psi and an output function G. Since if the original transition reads a symbol X and outputs some symbol Y, its inverse should read Y and output X. So the lookup of the inverse transition should be the size of the original output functions. And then the predicate of the inverse transition should determine the output of the original transitions. And at last, its output functions should recover the behavior of the original output functions. Our main theorem shows that if we can invert all transitions in the symbolic transducers, we will produce the inverse of the transducers. And the inverse is also a transducer. Now, let's try to compute the inverse of it, the transition. We need to first compute the predicate psi, and we already have the formula for the psi. So what we need to do is to delimit the quantifier in the formulas. If our background theory or the meter quantifier eliminations, we can use the quantifier elimination to generate the quantifier-free formulas, and this is indeed the case for B-vector arithmetic. But computing the output function G is more complicated. Since we don't have the formula for G, we only have a formula describing the behavior of G. Fortunately, the syntax guide synthesis can help us. Let me tell you what is the syntax guide synthesis SyGuS is by this simple example. In this problem, we want to synthesize a function max. So we first provide the context-free grammar, which describe the solution space, and then we give constraint formulas which tell the solution that we want a functions the function should output either x and y, and then at last we expect the solutions to output to give our solution that the max is a function that it output x if the x is greater than y, otherwise it output y. Similarly, we can build a SyGuS problem to compute G. The context-free grammar is the terms in our alphabet theories, and the constraint formula is something we already have. Then, the completeness theory shows that if the background theory admits inverse, the SyGuS will finally fire solutions for us. It will finally compute G. With knowing how to check injectivity in inverse transducers, we build a tool Genic to perform program inversions and for experiments. Genic is a domain-specific language which reads programs such as encoder as an input, and it compares it to symbolic transducers, and it checks if it is injective. If the answer is no, it can give a counterexample to the users. If the answer is yes, it will try to invert all its transitions and give and produce the inverse of the encoder E. Since the running time of our method is heavily depends on the solving time of the SyGuS problems, we use two optimizations to reduce the size of the SyGuS problem and speed up the solving time. The idea of the first optimization is to first inverse all injective or oxidative functions. We first invert oxidative functions, and then we add the inverse of oxidative functions to the context-free grammars in the SyGuS problems. And such kind of divide and conquer method will lead to several small-size SyGuS problems, and which is easier to solve than one single large SyGuS problem. And besides, an oxidative functions may be used in more than one place. For example, here the oxidative function E is used in 9 places, and if we don't invert it in advance, we need to invert it 9 times in the SyGuS problems. The second optimization is based on the observation that we might not need all output characters to recover a single input character. In this example, the transition T read 2 characters and output 2 characters. But if we want to recover the character x1, we only need the output character y2. So we can synthesize, we can invert the transitions in parallels for recovering x1 and x2, and the SyGuS problems only involve a smaller set of variables. Now we know how to invert programs, and we build a tool Genic to invert programs. The last question, what is the performance of our method? There are 3 things we may want to know about Genic. First, can Genic invert realistic encoders and decoders? Second, optimization we introduce necessary. And the third question is the output of Genic readable? To see if Genic can invert realistic encoders, our experiment tries to check the injectivity and invert 7 pairs of widely used encoders and decoders. Although the number of transducer states are small, the size of the programs is about 1 kilobyte, and which means that they are not easy to write them by hand. And they operate on the B vectors 8 and B vectors 32. The most important result is that we can successfully invert most of the encoder and decoders, except for 1 transitions in the UTF-8 encoder. Then we ask, how long does it take to check injectivity? No more than 10 seconds. And what is the solving time, the inversion time? The answer is from 2 seconds to 2 minutes. And if we use the parallel inversions, the running time will be 1 second to 1 minute. And the second question, are the optimization necessary? The answer is yes. This diagram shows that the running time, the running time grows along to to the size of the target functions, and we cannot synthesize the functions with 25 terms or more. However, without the first optimizations, the size of target functions could be very large. And the last question, is the output of the Genic readable? The answer is also yes. The inverse of program we produce by Genic is no more than twice to the inverse written by hand. So we can just use this automatic method to produce inverse of programs for practical use. In conclusion, we present a framework of inverting programs using transducers and provide a practical implementation based on SyGuS and SMT solvers. More paper about symbolic automata and transducer can be found in this link. Thank you. Mm-hmm.
How should I decide which one I'm going to write and which one I'm going to have your tool create from that?
You can write either one and use this to produce its inversion. It doesn't matter.
Really matter which one I start with?
Yeah, yeah.
Hi.
Hi.
I was wondering, so in the case of inversion, you usually have a case that encoders cover more. Suppose an encoder covers all strings,
Mm-hmm.
whereas a decoder actually applies only to subsets. So there is naturally a domain associated with the encoder as well as the encoder. So my question is, how is that taken into account in making this analysis?
In this case, first of all, the encoder is not injective, but we can still try to invert it on the partial set of input. We will get a partial behavior decoders, and which means that we can map the range of the character the strings in the range of the encoder to its inverse, but we cannot map anything outside of the range.
So essentially, the answer to that question is usually it would make more sense to look at an encoder because its domain is more inclusive than a decoder, then you can avoid partiality.
Yeah. But for the non-injective case, yes. But
I have another question unrelated. So how does the size of the language that you use, for example, in this example, I don't know if you don't have it yet, but you didn't include operations like shifting and matching or actually masking. So these are very often used in different.
Yeah.
What if you add those? How would that affect the time of
It doesn't. There's no specific relation between the shifter operation and the running times. We support the shifter operations for if the SyGuS solver support the shifter operations, our implementation can support it. But in theory, I think it's not a big problem.
So if I understood correctly, you write an encoder and then you synthesize the decoder. The decoder is something that rejects kind of invalid encoding. Then would it make also sense to allow synthesizing decoders that are kind of undefined for the invalid encoding to possibly more performance out?
Sorry, I don't understand.
So your decoder will reject invalid encoding if you written an encoder and synthesize a decoder.
Mm-hmm.
Right. Would it be possible to synthesize a decoder that's just kind of undefined or doesn't do anything meaningful for the other encoding to get more performance, not having to check that the encoding is valid if you happen to
Yes, I think if we extend if we try to collect more input from the user, we can do this.